Welcome to the LIUniverse. I'm Dr. Charles Liu. You can call me Chuck if you'd like. In fact, please do. Uh, and it's such a pleasure for us today to have this wonderful guest from CERN, the world's largest machine. And I can't wait for you to meet her and we'll talk. Dr. Lesya Horyn at CERN. Hello. Want to say hi. And of course, with us, our co host, Allen Liu.
Hello.
Lesya, hi.
Hello, thanks for having me.
Oh, thanks for
Okay.
joining us from sunny Switzerland. Well, as usual, we start today by sharing the cosmically joyful, cool thing of the day. And this particular one comes from not Switzerland, but that other place that does particle physics. And I don't even mean Fermilab in Illinois, Long Island, New York. At Brookhaven National Laboratories recently, some scientists figured out that indeed it is possible to make matter from energy, as opposed to energy from matter, which we've done for a long time using nuclear technologies and so forth. But the actual process of taking two pieces of light, two photons, and smashing them together and producing a matter antimatter particle pair was confirmed just recently at Brookhaven. I think that is super amazingly cool. Alan, now you, having had some experience with particle physics some years ago, you worked on some data at Brookhaven, right? You have a sense of how significant and cool this is, right?
Yeah, so I mean, Lesya, we know that the matter is created from energy all the time, sort of indirectly during particle collisions, and that's what makes all the particle physics stuff happen. But I think it's really cool that it's happening with photons and not particles that actually have mass. What do you think about it?
Yeah, I think it's really cool. At CERN, we collide protons, and we collide protons at super high energy, and so you can make things that are much, much heavier than protons. And so it's kind of like the main crux, I think, of particle physics is, especially now, right, is making these collisions out of things that we can handle that are quite light, and you can make all kinds of crazy heavy particles that we're looking for. And so I think this RIC result is really neat. It's cool. Studying all these different things with the photons, I think it's really interesting.
Right. In out in the universe, of course, pair production happens naturally. You have one extremely powerful photon with enough energy to make two particles, and they just spontaneously turn into, for example, a positron and an electron or something like that. That kind of pair production does happen all the time. But here, we actually have the ability now, it seems, to guide two photons that don't have enough energy together, but actually guide them to hit one another, and then from there produce an antimatter-matter pair, which I think is amazing. And what next?
Yeah, there were actually maybe last year, a few years ago, there was a new phenomenon, I suppose, observed by ATLAS and CMS. Most of the year, the LHC collides protons. But for the last couple months of the year, they collide heavy things. So sometimes it's lead and lead. They've collided lead and a proton. Sometimes they'll collide xenon. And usually when you see those collisions, it's like this huge mess, right? Because you make a big mess with the protons and the detector, right? You get big sprays of particles everywhere. And then if you have something with as big of a nucleus as lead, you can just imagine it makes a huge mess. And this is a lot of what they do at RIC, I think, is that they collide. At the end of the last run of the LHC, when they were colliding lead, they decided instead of colliding them to kind of make the collision point a little wider, so that way you would have the lead nucleus not necessarily hitting head on, but kind of nearby. And so the goal here was for each of the lead particles to emit a photon, to radiate as they were passing through. And then you can observe observe light by light scattering, right? So you observe photons scattering off of each other. And so instead of having this big, really messy events, you just have this really cool signature of just the photons that have scattered against each other in the detector. And that was really neat. I think it's cool to use this really messy thing to observe kind of I think it was used in a really creative way.
That's
I think it's a
fantastic. Yeah.
really cool study. Yeah.
Yeah, because lead is 200 times heavier than a proton typically. And so that
Yeah.
glancing blow can produce all kinds of neat things happening. But right now, it is time for Allen to feed us a question from our students or our patrons. Allen, who we got?
So we're going to start with a student question today.
Okay.
This is from Lindsey from Massachusetts. And Lindsey asks, do you believe there is an elementary particle responsible for gravity?
So, yeah, it's a good question. I think that different people have different opinions, but right now we kind of have what's called the standard model. So it's kind of like the periodic table of particles. And, we know that it describes the things that it describes very well, and it's missing big pieces, right? And so the discovery of the Higgs boson was the last piece in understanding that periodic table of particles that we kind of already knew about and guessed were there. And now, unfortunately, that periodic table of particles makes a really nice picture, right? It describes things super well. It describes things really, really excellently well. But it's missing stuff, right? That we know that dark matter exists, not in the standard model. We know, and we know that gravity exists, right? But that's not in the standard model either. In a lot of these beyond the standard model theories, you have what's called a graviton, which is like an elementary particle that would be responsible for the gravitational force. In the same way, you have a photon that's responsible for the electromagnetic force. And so I would say that it is one of the things that people search for, and I think it exists. I would hope that.
Yes.
I hope so.
You heard it here, folks. Lesya Horyn, Dr. Lesya Horyn believes that gravitons exist. Excellent.
I hope so.
It seems to make sense to me too. We can talk all about the scientific reasons why most astronomers think gravitons exist, but we will leave it at that for now because there's so much to talk about, and I think that's really true. Thank you. And by the way, in Marvel Comics, there is a supervillain named Graviton. Okay, and I just so in that other very important way, gravitons do exist, or at least one of them does. Never minding that.
Does he have the power of gravity? Is that
he has the power of gravity. Yeah, to pull stuff back and forth. But of course, it's comic book pseudoscience, so we have no idea if he's actually using quantum particles like gravitons, or if he's just bending space-time, general relativistically or something goofy like that. So, we'll see where it goes. Okay, thanks for that great question. So that really does launch us nicely into your research, Lesya. Tell us, please, just what is your research? What do you focus on? I'll tell the audience as a bit of background. You got your undergraduate degree at Tufts University, you got your PhD at University of Chicago, and then now you are in Switzerland doing this research. So tell us what it is that you do.
Yeah, so now I work with Fermilab, but still work at CERN in Switzerland.
And Fermilab is where?
Fermilab is in Illinois.
Okay.
Yeah.
So near University of Chicago thing.
Yeah, but there's lots of institutes across the U.S. That participate in the in science at the LHC, right? And so there's one of the main experiments around the LHC, which is the Large Hadron Collider. And so it is a big ring underground, made of a tube and magnets that they use to collide protons. Very, very complicated magnets, series of different rings and magnetic fields to make the protons go at the energy that we want to study them at.
And how big is this ring?
The ring is 20 kilometers around.
12 miles.
It's 12 miles. Yeah.
Amazing.
And so now I work, I used to work on the ATLAS experiment, which is kind of near the main site of CERN. And now I work for the CMS experiment, the compact muon solenoid. And that's on the other side of the ring. And so you have to really drive 20 minutes to get from one to the other. There's a bike path that takes you around the whole ring, but it's just under towns, and I don't know, it's kind of funny.
Amazing.
Yeah. And so these two experiments, Atlas and CMS, were kind of designed independently to do the same thing, because you want to be able to, verify any results that you see. Because to do the kind of physics that we're doing, you need this really complicated, really high energy machine, and really the LHC is the only environment that you can do exactly the kind of science that we're doing. The whole system was designed with a way to provide kind of somewhat independent verification. So, for example, if so you would expect that if one experiment, one collaboration discovers something or measures something, that you would expect the other experiment to do so too. And so the detectors are designed, they have different priorities. And so I think actually, now that you're saying it, a lot of the letters of CMS contrast it to Atlas. And compact in that it's much smaller. And the whole thing is inside the magnetic solenoid.
Whereas Atlas is huge, right? I mean, I've seen pictures of that thing. I mean, it's like a person is dwarfed by that.
Yeah, it's really huge. CMS is also huge, right? Don't let this conversation deceive you. It's smaller than Atlas, but very large. It's a very large thing.
So does Atlas stand for like ultimately large, super gigantic?
It is a really terrible backronym. It is a toroidal. So the toroid is a kind of magnet. Atlas also has a solenoid, but they also have a toroid. Okay. A toroidal, LHC, for apparatus. And they take the S from the end of apparatus.
That's almost as bad as astronomers' acronyms.
Oh, yeah.
I'm sure it's the same in astronomy, but I really love going to talks about experiments I've never heard of and just like trying to figure out what is like the most horrifying acronym that people have used. There's one proposed new experiment around here, around the LHC, that's called Methuselah. And you can just imagine.
That's an entire acronym? Holy moly.
It's an entire acronym with letters generously picked from the center of many words.
Yeah, astronomers, we just gave up and started naming telescopes after people. And that makes it a little bit easier, but still, it's not as much fun, I have to admit.
Yes, it really requires some creativity.
So the CMS and the Atlas are basically yin and yang. They are
exactly.
One, I know.
I don't think they're good and evil, but I mean that they are. They were designed by different people. They're run by different people. For example, CMS has a better tracker, and Atlas has better calorimeters, so the things that measure the energy of the particles. And so there's just different choices made about how the detector was designed, and so you can do different kinds of things better or worse, but they both do incredibly well. So if like Atlas had seen the Higgs boson, but CMS didn't, it would have been a big problem. I think it would have been very confusing. I think it would have been much harder to trust the results, and so.
Well, when the discovery of the Higgs boson happened, that was like international news. They did it on the 4th of July, so there was no other news going on in the United States. It just sort of splashed. And both CMS and Atlas, an amazing discovery. And there were people like in tears in that conference room. I remember watching the video feed, like Peter Higgs sitting there was literally like dabbing away moisture from his eyes and stuff, because it was such
It's incredible. It's really incredible, I think. Yeah. It's actually the 10-year anniversary this year, if you can believe that.
Oh, wow. Has it been that long? Holy moly.
Isn't that crazy? It's really crazy.
Were you even in graduate school 10 years ago?
During my undergrad. Yeah, it was during my undergrad.
We won't even give an estimate of how old Allen was 10 years ago, or how old I was 10 years ago, because that's not important, obviously. But it's amazing. It's been 10 years, and the Higgs boson itself, the discovery allowed us what? Helped us understand what?
Yeah, so I think that the Higgs boson really, so it really filled in the last piece of the standard model, right? That it kind of shows that this theory exists, that the way that we thought the whole thing worked is actually how it works. Now people really think about the Higgs boson almost as a tool, because the Higgs boson can decay into all the other standard model particles because it interacts with all of them.
Oh, really?
Wow.
Yeah, and so there's this cool plot that shows you kind of as a function of the mass of the Higgs, you know exactly how often the Higgs should decay into each of the standard model particles. So, for example, you say that you know that it should decay into photons X% of the time, and so that's a statistical thing, and you can measure that. And so one thing that people really want to do for the future, kind of thinking about future experiments, is to measure really precisely the kind of the decay modes of the Higgs boson, because anything that this kind of the Higgs going to the leftover piece, the Higgs going to something that you can't observe, can tell you something about what kind of physics might be beyond the standard model if those kinds of particles would also interact with the Higgs.
Can you find dark matter?
I think so. I think that I don't know that if so. I think that if you found out that the Higgs we call it the branching fraction, how often the Higgs decays into a given particle. So I think that if you found out that those were super wrong in some way, or that there was really something missing, I think that you wouldn't find dark matter explicitly, but you would launch a million theories and have a million things to measure of different ways, and hopefully you find dark matter that way. There's lots of people looking for dark matter. I do promise that lots of people looking for dark matter. It would be very nice to find.
Work hard, would you please? Because we really would like to know what it is. but is that does that mean that like the standard model is done? We found the Higgs boson. Yay, we can all go have a drop of sweet beer or something, and then just, are we done with particle physics?
Certainly not. Most certainly not. Also, as we were talking about with the first question about the graviton, right? That if I really think about the goal of particle physics is to be able to write down the equation, the list of particles, whatever that the universe is made of, right? That if you start from this list, you can explain everything, right? And obviously, it gets very complicated, and you use better kinds of tools to explain everything later on, but that you want the distilled list of stuff that you can start with. And so the fact that we know that dark matter exists and there's no way that fits into the standard model. So you can say that, I guess, that maybe you can say the standard model is done, but particle physics has a lot of work to do.
I like that.
Yeah.
That makes a lot of sense. Tell us a little bit about this experiment that was done at Fermilab recently called the muon G2 thing. I think that's what it was.
G-2?
Yeah, G-2. Yeah. Okay. So yes, the muon G-2 experiment, I think, is a super neat experiment. And it relies on the same kind of thing that we were just talking about, as measuring, the Higgs decaying. And it fits into the same kind of category of particle physics work, where you want to measure something super precisely.
Okay.
And you hope that knowing that the exact number of something, knowing to many decimal places with a very small error, can tell you something new about how particle physics is structured.
Okay.
So in the name, so muon is the kind of particle that you want to measure, and the muon has a property that people label G. And so it's the gyromagnetic moment. It's not important, but it's a fundamental.
It's very important.
So it's a gyromagnetic moment, and it is important for the experiment because it tells you about how the muon will move in a magnetic field. The idea is that if there is only standard model physics, the G, the number associated to the muon, should equal 2. And so any deviation from 2 is a deviation from the theoretical prediction from the standard model.
So it should be exactly 2.00000000.
Yeah.
Okay.
And so any difference from that should tell you something about physics beyond the standard model, right? Because it doesn't fit into the standard model. And so that is the goal of this experiment, is to measure this number extremely precisely. That's kind of hard to do because muons decay. They don't live too long. And so you need to have muons close by. You need to, have this big magnet to measure how they behave inside that magnetic field. And then you can measure this interesting number.
So how long do they live? How long do muons live?
2 microseconds.
2 microseconds.
Yeah. And so it's very shortly lived. And so you really have to have them close by. And so you can only really do that in a few places in the world, right? You need a reactor, you need the kind of all of the physics infrastructure to be able to do it. And so when they first did this experiment, they did it at Brookhaven. And at Brookhaven, they ran the experiment for a while and they measured this number. And they found that it did not agree with the standard model, but they didn't have enough data to actually say that definitively. There's kind of a standard across the community of kind of what percent probability that whatever you observed is
believable.
Well, yes, exactly, right? That you need to say that there's a extremely small probability that the thing that you observed could have happened by chance, right? Because in the end, you're measuring statistical effects, right? And so there's always some chance that what you saw was just a really weird statistical thing, and not actually something new. And so there's kind of an agreed upon standard for how sure you have to be. And so Brookhaven got pretty sure, like probably not just an obvious statistical fluctuation, but not sure enough to be able to claim discovery. And so what they did is they basically took the giant magnet from Brookhaven, put it on a boat, drove around the bottom of the U.S. and up the Mississippi River, and then brought it to Fermilab. Which is crazy. Yeah, but that's where the muons were at the time, and so they redid the experiment. And so yeah, I think it's crazy. I think it's really cool. Yeah. They have all these pictures of this huge magnet that took up, the whole highway, right? They really had to close the roads and bring this thing down into the lab. I think it's cool. I think it's crazy. And so they're redoing the experiment. So now they have released their first results. I think that they're going to continue to take data and release more results. But they found a deviation from the standard model now that agrees with the Brookhaven result and is now at the statistical significance needed to say that it's something different.
So G-2 is not 0. Is that right?
It's not 0. It is very small. I'm not sure exactly how small. I think it's very small.
Yeah. Okay. Just gonna jump in. Don't want to interrupt too much, but I found the G-2 values.
Ooh, yes.
Good.
The predicted value for G-2 for the muon is 0.00116591804, but the experiment says it's 0.00116592096.
Oh my gosh!
So that's a lot of digits,
and it's a lot of decimal point. Yeah.
And that difference is a signal of new
physics. Yeah.
I think it's crazy that a number that big or a number that small with that many digits, right, can tell you stuff that it's really worth a lot of people spending a lot of time and to do, right? I think it's really cool that you can really learn so much from knowing something really, really exactly. I think I think it's really remarkable.
That's fantastic. I can't. I can understand why you do this because that sounds like such amazing frontier stuff. Let's take at least one more question. What do we got, Alan?
This is a question from Walter T. from our Patreon.
Oh, wonderful.
He's asking, could the many worlds theory still be deterministic? Like if the world split, but with enough data and knowledge, the split was always expected.
Oh, Walter, you are just not laying it easy on us. But let me just say, for those of you who don't know about the many worlds interpretation of quantum mechanics is an idea that was proposed some decades ago. The idea that every single moment, every single time something happens in the quantum universe, a whole new universe splits off, right? And then you wind up with all of these universes all over the place. And so Walter is asking if it's deterministic. Okay, Lesya, you have to take this one from here.
I was thinking about this, and the only thing that comes to my mind is there's a famous quote from Richard Feynman that says, "Anybody who claims to understand quantum mechanics is either crazy or lying." And so I have no idea.
That's amazing. Yeah. Could everything come back together? That's just wild speculation, basically, from your point of view. There's nothing really that's giving us any knowledge about this yet.
I guess the thing that I don't know about the kind of many worlds theories is, and I think a lot of these kinds of interpretations is there actually something that you could measure? Is there actually any, it's nice to think about, but I think that really what matters is, and I think that people debate this a lot about kind of different called grand unified theories, right? Or theories that will, fix the whole thing, right? That is that there's a lot of things that are nice and interesting ideas and mathematically interesting, but at the end of the day, you need to have something observable, right? You have to have in order to say yes or no or make any kind of statement about it, that you need to think of something to measure, right? And I have no idea.
I think that's beautiful. That really does encapsulate the difference between speculating about possible scientific things and actually thinking like a scientist would. What can we measure? That's just a great way to put it. That's fantastic. Lesya, tell us how we can follow you and know all the cool things you're doing and the things that are coming up with you.
Yeah, so you can follow me personally on Twitter at LESYAAH. And I would also encourage you to check out the social medias of CERN and the Atlas and CMS and all the other experiments at the LHC, because the LHC is turning back on in the next few months. And so hopefully there will be lots of news to follow, and we'll have a fresh new data set and new stuff to look at and much more physics to do. And so definitely stay tuned. It's going to be an exciting time.
Wow. Fantastic. Thank you so much, Lesya. And thank you all, everyone, for being part of this episode. It has been such a pleasure. Lesya, thank you again so much for being here with us.
Thank you. Thank you for having me.
Allen, thank you so much for all that you do. Really appreciate it.
Yep.
And for all of you, if you like what you hear, go to Patreon, support us. We'll get more episodes out. We'll have more fun with this, and you get your questions answered too. Thank you all so much for joining us. Thank you for being a part of the LIUniverse.